Welcome to Study Loop.
We are given a bipartite simple graph, and we are asked to prove an inequality between the number of edges and the number of vertices of this graph. So let G be a simple bipartite graph. Let V be the number of vertices of this graph, and E be the number of edges. Now, since G is bipartite, it follows that the n vertices, not n vertices, but V vertices partition into two sets V1 and V2, and so if we have that, suppose set V1 contains n vertices, then it follows that the set V2 will contain total number of vertices V minus the number of vertices in V1, which is n, so V minus n. And we have that every vertex in the set V1 can only connect with vertices in V2, and vice versa. So it follows that if V1 lies in set V1, then it follows that the degree of V1 must be less than or equal to V minus n, and there are n vertices in V1, so the max number of edges, and this is going to be a function that depends on that value n that we chose for the size of V1. This is going to be the n vertices, so the number of vertices in V1, n, times the maximum number of edges, which is going to be V minus n per vertex. So we get n times V minus n, and just to simplify this, I'll write this as a function f of n, and we want to find an upper bound on the number of edges, and to do this, we want to find the maximum number of edges and maximize it. So it follows that the derivative of the maximum number of edges, f prime, with respect to n, this is going to be v minus n plus, instead of a plus, this really should be a minus n, which is v minus 2n, and we want to find the critical values. So set this first derivative equal to 0, and we have that n is equal to v over 2. So the maximum, we know, occurs at n equals v over 2, and we have that f of v over 2 is equal to v over 2 times v minus v over 2. And this is the same as v over 2 squared, which is v squared over 4. So the maximum number of edges is v squared over 4, and so it follows that the number of edges in the graph, E, is less than or equal to v squared over 4. And this is what we wanted to prove.